Hello, in this video we're going to see proof by induction. Mathematical induction is particularly useful proof technique in computer science. It is used to prove some statement true about all the integers greater than or equal to some fixed value. There are two principles of mathematical induction. We're going to see the first one. So the first one, the steps are very simple. You prove the base case. For example, for all n greater or equal to 2, first case will be n equal to 2. Then you assume the property is true for n or k. And then the last steps is you're going to try to prove for n plus 1 or k plus 1. In my examples here, I'm not going to use k. I'm just going to keep it as n. So it says prove that 2 plus 6 plus 10 for n minus 2 is equal to 2n squared for any n greater or equal to 1. So the first thing is, this is the first principle of mathematical induction when I'm dealing with an equal sign. Okay? So the first thing I do, 3 simple steps, I'm gonna check for n equal 1. Because that's the smallest n, that's the base one. The base case is n equal to 1. So as you see, you have one term. When n is equal to 1, basically you have 4 times 1 minus 2. That's my first in the sequence here. So is this really equal to 1 squared? So as you see, you have 2 for minus 2, and here you have 2. So this is 2. So 2 equal to 2, then it works for the smallest n. So first you check for the smallest n. The second thing is that I'm going to assume that for all n greater or equal to 1, 2 plus 6 plus 10 plus all the way to 4n minus 2 is going to be equal to 2n. So I assumed whatever I'm going to prove. And 3, I'm going to try to prove that for all n greater or equal to 1, 2 plus 6 plus 10 plus all the way for n minus 2 plus the next term after 2 for n minus 2 is that you replace n with n plus 1. So if you stop at n, the next number will be n plus 1. So it will be 4 n plus 1 minus 2. It's equal to then n plus 1. So check for n, the smallest based one, in this case n1. You assume for all n and you prove for n plus 1. That means you prove the next term will hold. This a summation will hold as well. This formula holds for the next n. That's what we're trying to do. Okay, so what I need to prove, this is a question mark. That I go from the left hand side, I get to that right hand side. Okay, so this is what we're gonna do. The left hand side, it's equivalent to, so all of this right here, 2 plus 6 plus 10 plus all the way to 4n minus 2 is equal to 2n squared from my assumption. So this is, I'm going to say, from the assumption, I replace 2 plus 6 plus 10 all the way to 4n minus 2 with n squared. That's from the assumption. Then what's left is that plus, if I distribute here, I get 4n plus 4 minus 2, which is basically 4n plus 4 minus 2, which is plus 2. Okay, so again, this is your left hand side. What is this left hand side equal? So if I factor the 2 out, it's gonna be n squared plus 2n plus 1, which is equal to 2n plus 1 quantity squared. I just factor n squared plus 2n plus 1. Now what do I have? This is equal to the right hand side. That's what I need, right hand side. So I went from left hand side to the right hand side. We're using the assumption. So now we proved for n plus 1. So it works for n plus 1 using the assumption, and thus for all n greater or equal to 1, if I add 2 plus 6 plus 10 all the way to 4n minus 2, I will get 2n squared. This is a formula for it. So as you see, this is an arithmetic sequence. If you took a pre-calc and you went over arithmetic sequence, so this is an arithmetic sequence where you go from one term to the other by adding 4. And so the summation for this specific arithmetic sequence with the starting at 2 and adding 4, it will up to n. When you add all the way to an, you get 2n squared. Now we prove it using proof by induction. This is how it works, proof by induction. 3 steps, very simple. When you usually the third step, you have to use the assumption to go from one side to the other. This is for the first principle of mathematical induction. Next time we're going to see the second principle where you have less than, greater than. But for now we have equal, therefore it's going to be the first principle of mathematical induction. Let's see another example. So let's see another example. Here we have prove that 1 plus 2 plus 2 squared plus all the way 2 to the n is equal to 2 to the n plus 1 minus 1 for any n greater or equal to 0. So first I'm going to check if true for the base one, which is n equals 0. See, I have n starting at 0. So my first, you replace n with 0. So you get 2 to the power of 0. Is this really equal to 2 to the power of 0 plus 1 minus 1? Let's see. Anything 2 to the power of 0 is 1. And this will be 2 minus 1, which is also 1. So it works. We checked one for the base n equals 0. Second thing, I'm going to assume whatever I need to prove, that for all n greater than or equal 0, 1 plus 2 plus all the way to 2 to the n is equal to 2 to the n plus 1 minus 1. And number 3, I'm going to try to prove that for all n greater or equal to 0, 1 plus 2, but we don't only stop at 2n, we add one more, which is going to be 2n plus 1. So you take n, replace it with n plus 1, and we must be equal to, again, if I take n, replace it with n plus 1, you'll have n plus 1 plus 1, which is n plus 2, minus 1. So this is where we need to prove. If we prove this, we're done with the proof by induction. So again, the left hand side equal. Here is the left hand side. So again, this is the same as this, which is equal to 2n plus 1 minus 1. This is from, you must state that, from the assumption 2 to the n plus 1 minus 1. Then we're going to add 2 to the n plus 1. Is this really equal to, that's the question mark, 2 to the n plus 1 minus 1. So if I rearrange this, I have 2 to the n plus 1 plus 2 to the n plus 1 minus 1. So if you think of this as x, for example, some variable x, so almost you have, what is x plus x? That will be 2x or 2 to the n plus 1 minus 1. Now we're just using the law of exponent. So we have the same base. So what we do here, you add the exponents. So where is it going to be? It's going to be 2, 1 plus n plus 1, which is n plus 2. You remember 1 plus 1 is 2 and n plus 2 minus 1. So we stop here and we say this is what? This is the right hand side. So what we did, logically, we went from one side, we end up at the other. So it's true for n plus 1, and therefore it's true for... Let's see one more example. So we have 1 squared plus 2 squared plus all the way to n squared is equal n plus 1 to n plus 1 over 6. This is the summation of squares. So that's the formula for it. It depends where you stop. If you stop at 5 squared, that means you replace n with 5. So 1 square plus 2 square plus all the way to 5 square will be 5 times 5 plus 1 times 2 times 5 plus 1 over 6. So this is a formula for the summation of squares. But let's prove that this is always hold and is always true. First thing I'm going to check, n equal 1. So as you see here, this is 2 times 3, which is 6. So it's 6 over 6, which is 1. So 1 equal 1, we are done. Number 2, I'm going to assume for all n greater or equal to 1, 1 square all the way to n square is equal n plus 1 to n plus 1 over 6. Number 3, I'm going to check for n plus 1. So what does it mean? Replace every n with n plus 1. So n plus 1. N plus 1 plus 1 is n plus 2. And replace n with n plus 1. So it's going to be 2n plus 2 plus 1, which is 2n plus 3. So again, distribute the 2 with the n plus 1. That's what we need to prove right here. That means you go from the left hand side and you must get to the right hand side. So as you see, the left hand side is equal to what? So right here, this is the assumption. So I would say that from the assumption, 1 square plus 2 square plus all the way to n square is equal n plus 1 to n plus 1 over 6. Then I have one more term to add here. Now my goal is to go from this side and up at this side. So with the letter algebra, let's see if I do the least common denominator here. I get n plus 1 to n plus 1 plus 6 n plus 1 quantity square. So I have addition here. So I have n plus 1 twice and I have n plus 1 here. So I could factor n plus 1. So here I factored n plus 1. So what's left, or if you divide this term by n plus 1, you have left n times 2n plus 1. And if you divide by n plus 1 here, you get 6 times n plus 1. Again, if you multiply through, you go back here. Over 6. And remember, my goal is to end up at the right hand side. So if I distribute one more here, so here I distribute, now I'm gonna add the like terms, and then as you could see, you could factor the 2n squared plus 7n plus 6. So if I factor that, I will have n plus 2 times 2n plus 3. Of course, over 6, which is the same as the right hand side. So again, we went to move from the left hand side. We use the assumption of parts of the left hand side, replace the dot with the assumption, and then add the n plus 1 term. Do some algebra, factor in and so on, and you end up at the right hand side. And therefore, now we're done. We can say that 1 square plus 2 square plus, and we're done. So remember that for your proof to be correct, you must write all the steps now to 1, 2, 3, and then you must show all the work because it has to be logical and equivalent from one step to the other.